All right then. Hi everybody. Welcome to a new beginner track workshop. Today we'll be talking about multi-class classification. You can access the slides through the feedback form linked in the slide right here. And if you haven't joined our Discord yet, then please check it out. So because we didn't cover logistic regression last week, we will start by giving a brief summary of what logistic regression is. So we've seen linear regression before. So given the input features of an object, we want to see the probability that the object belongs to either of two classes. So let's say we're able to figure out the probability of an object that belongs to class 1. So how could we use that to get the probability of an object that belongs to class 0 from this? Well, in this case, we would just subtract it from the probability that's in class 1. To do this, we need a hypothesis to find this probability. In case you've forgotten what a hypothesis is, it's essentially a model or some sort of equation that describes a solution space that we need. And in this kind of case, where you're not deciding between two classes as in like features, but instead looking for the probability, we are going to use something that's called a logistic regression model. So you may or may not have seen a function that looks something like this, and we call it a sigmoid function, which has an equation like this. It's not too important. You just need to memorize the general idea of it. Essentially, sigmoid function splits off this line into pretty neat places, as in if x is negative, then the sigma of x will be less than 0.5. However, if x is positive, sigma of x will be above 1.5. Now, why does this matter? Because sigma of x only goes from 0 to 1. Now, probability also goes from 0 to 1, which means that if x is negative, the return value will be less than 0.5, meaning that it's less likely. While on the other hand, if x is positive or even really big, then that means that it trends closer to 1. So this makes the sigmoid function pretty ideal for modeling a probability distribution. And that's where logistic regression comes in. As we've seen with linear regression, an input needs to be classified as 0 or 1, or in this case, it's a binary classification. So we need to find the decision boundaries or the weights and biases, as we've seen before, for our model, which is known as binary classification. Now, we've seen this symbol y hat before, and you might remember that this is our predicted value. So we had the sigmoid function, which is this general shape. However, now we'll get something that is the prediction for the possibility of between two classes. So now we have a prediction that we can then use to form a probability. Now, probability in this case, we want to measure something that might be one class or the other, as I said before. So therefore, y hat is really just a bunch of decimal points, or in this case, kind of like percentages, that basically when the input is in a given class. So to expand on this equation, we're going to define this as y hat is the probability, or in this case, p, that the label y is 1 given the features x that we have. So this might look like a complicated equation, but don't worry, it's mostly just a probability equation. I see we have some new people here. If you have any questions about the things I just went over, because you might have missed the first couple of slides, and just put them in the chat. Thank you. So bringing in another thing that we may or may not have seen in linear regression is we have loss functions, which you might remember with the notation L of Y in the prediction. Now, the loss function for previously looks a little bit different because we were updating our weights and biases. However, with this loss function, we now have our prediction of a probability, which is Y hat, along with the target label. So to break it down, if Y is 1 in this case, then as we all know, log of Y, log of 1, sorry, is going to be 0. However, when Y is 1, hopefully our prediction is close to 1, or at least closer to 1 than it is to 0. So therefore, our loss function will instead become the negative log of Y hat. And in a similar case, when Y is 0, then log of 0 is undefined, I believe. So Y hat hopefully will be closer to 0 than 1. So we will be taking the log of 1 minus Y hat, which will give us a valid answer. Now, another familiar topic to you might be gradient descent. There's not too much different between the gradient descent that we saw in linear regression and in logistic regression, even though we have the sigmoid function instead of a linear line. Instead, now we are having a vectorized form of the partial of the weights and the partial of the biases, because now we have a vector of all of these probabilities. So we have very similar step size. These might look familiar to you, and an ultimate equation for updating our new weights, our new biases. So remember, Y hat is a column vector with a size of m, which has all of the predictions or probabilities. And Y, the target, is also a similar size vector. And we have all of our target data, which is X. So since Y and Y hat are the same size, this will subtract into one vector that will give us a form we're quite familiar with. So we've linked the full derivation if you want to know more. However, you don't have to know too much other than the main equations on the right here, which have the weights and biases. And remember that this looks quite similar to what we've experienced in linear regression. Oh, and we got it from torsdatascience.com. So in case you want me to go back to an earlier slide, because if you came in late, you probably didn't see it, we're going to check to see if you know what logistic regression is good to use for. So let me, hopefully you guys can see it. Oh, another poll has started. And I'll give you a couple seconds for this. I'll give you 5 more seconds. Okay, so pretty split here. But the one thing we need to remember with logistic regression is that it is a probability between binary classification. So in this case, most of these are continuous, but approving or denying alone is 0 or 1, or yes or no. So logistic regression would be best for binary situations like that. in case you want to have a visual of what binary classification looks like, then you can click on this link over here, which will take you to this neural network playground. Now you can add neurons clicking on this, and you can have different features, as we mentioned before, as properties of things. And you can either click them or unclick them. And then you can mess around with all of these certain options to see the predictions of what area does the output think that the values are in. So you see that we have an orange area in the middle with blue on the outside, which isn't entirely correct, as you can tell by this data, but you can mess around with it and see if you can create something cool. And while you do that, if you have any questions or if you want me to go over anything again about logistic regression, then please put your question in the chat or feel free to speak up. Okay, and with that, then I'll turn it over to Jensen. So let me stop sharing my screen.
Okay, can you guys all see my iPad?
Yep.
All right, so now that you guys have hopefully mastered binary classification, let's go into multi-class classification. So for the setup for the multi-class classification problem, so let's imagine we have a bunch of photos of cats, dogs, chickens, and fish that we want to classify. So here we have 4 distinct classes. So this is where the multi-class comes into play. So recall in binary classification, so we either label our classes 0 or 1, or sometimes we also do -1 and 1, but that's less common. So in this example, a naive approach to label our classes would be to label 0 for cats, 1 for dogs, 2 for chickens, and 3 for fish. And let me write down this naive approach. So I'm gonna give you guys maybe like 15 to 20 seconds to identify like any potential issues with labeling it this way. Okay, so to illustrate why this naive approach might not be the smartest, let's go through a simple example. So let's look at this image of a cat here. So from this image, we know the label is 0 because it's a cat. And so if our model predicts the correct label, so if our model predicts 0 also, so actually we have to choose a loss function in this scenario. So for simplicity, I'm just going to choose mean square error, but mean square error is usually not the best loss function for classification, but just for simplicity, I'm going to use MSC for this particular example. So if my label is 0 and my prediction is also 0, then recall our MSE is just y minus y hat squared. So this would give me 0 minus 0, which is 0. So this is all well and good, right? But however, if our model predicts the wrong class, so for example, if our model thinks this image is a dog, whereas in reality it's a cat, then our MSE is going to be 0 minus 1 squared, which is 1. So this is still pretty reasonable. This has a larger loss than when our model predicts correctly. So that's still acceptable. So let's look at the case where our model predicts if this is a chicken, which is class 2. So the MSE would be 0 minus 2 squared, which is 4. So now you guys can probably see like what the problem is, because even though in these two examples, let me change here. So in these two examples, the model is predicting the wrong class, but the loss is very different, which shouldn't be the case, right? Because I don't think the model is any more wrong if it thinks a cat is a dog, whereas if the model thinks a chicken is a cat. So this doesn't really make sense, which is the motivation behind why we want to use one-hot encoding to label our images in a multi-class setting. So how this essentially works is for a single image, we can either assign a 0 or 1 to each category, depending on whether or not the image is under that category. So we have the following classes: cat, dog, chicken, and fish. So these are our 4 classes. So now we have an image of a cat. So is this image a cat? So the answer is yes. So we put a 1 here. And then is this cat an image, or is this image a dog? And the answer is no. So we put a 0 here. And I think you guys probably get the idea. So for these two values, it's also 0. And then next, we can put these labels into a vector indexed by each class. So recall we said cat should have label 0, and then dog should have label 1, and chicken should have label 2, and fish should have label 3. So these are our indexes for our one-hot encoded vector. So yeah, this matches what we have here on the right. And this whole process is basically called one-hot encoding. And there's some like nice property with like one-hot encoded vectors. So for example, if I have a label for a cat, a label for a dog, a label for a chicken, and a label for a fish. So if you look at these 4 vectors and you compute the Euclidean distance between any of these 2 vectors, they all have a distance of root 2 from each other. So that's one nice property. There's a symmetry between these. Okay, what am I writing? There's a symmetry between these labels that does not exist if we just label our images as 0, 1, 2, and 3. So yeah, that's the intuition behind one-hot encoding. So here are some more examples of images that are one-hot encoded. So just go through these one by one to make sure that they make sense. All right, so now that we have figured out a way to label our images in the multi-class setting, our model also needs to predict, or the output of our model, so y hat, recall. So this also has to have the same shape as our labels. in order for us to basically compute the loss. So in the binary setting, our y hat is just a number. So let's say a 0.9. But for the multi-class setting, we want our y hat, which is our prediction, to also be a vector. So ideally, we want our prediction to look something like this. So this would be a really good prediction because if our model makes this particular prediction, that means there's a 0.90% chance that our model thinks this image is a cat, which it is. And there's a 10% chance that this image is a dog. So this is an example of a good prediction. A bad prediction might be maybe 0.1 and then 0.5 and then 0.3 and then 0.1. So this would be a bad prediction because, as you can see, our model doesn't really think that this image is a cat when it in fact is a cat. So yeah, any questions with regard to like one-hot encoding and the setup for our multi-class classification? If not, I'm gonna do another review of our binary model. So under binary classification, our data x is a n-dimensional vector. So in particular, this would have shape n times 1. And here we're only looking at a single training example. So this is important because one single training example has like n features under this assumption. And so this would be an n/1 column vector. And our weight similarly is also n/1. And our bias is a scalar. So to compute the prediction, we take the dot product of our weight and our data. So W transpose X plus B. And then we also apply our sigmoid function. So this would give us our y hat for one single training example. So yeah, this should hopefully all be reviewed. So for our multi-class model, the input X is exactly the same because in this case, we're only adjusting our model, not our data. So this is also n/1. However, in the multi-class setting, our weight is no longer n/1. So let me write that down. So in binary, our weight is n/1, and our bias is 1/1 because a scalar. So yeah, in the multi-class setting, our weight is no longer n/1, but it's n/c, where c is the number of classes and n is the number of features in our data. So one way to think, or one way to motivate why our weight has this particular shape is to think of our multi-class model as C binary classifiers. So the first column in our weight would correspond to the weight of the binary classifier for class 1. And the second column would correspond to the weight of the binary classifier for class 2. And so you can think of each of these classifiers classifying like whether our image is class 1 or not class 1. So this would be class 1 versus not class 1. And then for the second way, this would give us a number that quantifies whether it is class 2 or not class 2. Let me highlight this as well. So similarly, our bias is also a C/1 vector. And this makes sense because, again, the first number here is the bias for our binary classifier for class 1. And the second value here is the bias for the binary classifier for class 2, and so on. And so to compute the output of our multi-class model, we do a very similar thing. So we take we multiply W with transpose with X, and then we add the bias. And then this will give us our Z, which is an intermediate value in this case. It's not our final prediction because we have to essentially activate this quantity Z to get our final output for the multi-class model. But the quantity Z is also sometimes known as logits in literature. So I'm also going to use the term logits to refer to this intermediate quantity Z. So yeah, so let's actually check the dimensions of each of these quantities to make sure that they make sense. So recall our weight has dimension n by c, so W transpose would have dimensions c by n, and then X has dimensions n by 1, bias has dimensions c by 1. So recall to multiply like two matrices together, you want their inner dimensions to match, which it does. So W transpose X is going to have dimensions c by 1. And as you can see, these two numbers have the same dimensions. So that means we can add them together for these two vectors. So we can add them together. So yeah, this passes our sanity check. So let's go through a more concrete example in the following slide to make sure that this makes sense. I think in this example, we generalize this to C number of classes as opposed to, this is just a more concrete example. So let's say we're given an image of a cat. So I'm going to say this image has 32 by 32. So in computers, like an image is usually represented as a 2D matrix of pixel values. So my cat image is going to look something like this. And this matrix is going to have shape 32 by 32. Let me write that down. And so the first step here is to essentially vectorize this into a one-dimensional vector. So what we do here is we just flatten this matrix into a vector that has shape 32 by 32, or 32 times 32, which is 1024 by 1. So this is our first step. And then the second step is we just pass this into our model, which has a weight and bias. So we just take the product between W transpose and X, which is our flattened image, and then we add a bias term. And so this would give us our logits, not prediction. So this is going to give us our logits Z over here, which is also 4 by 1, because we're assuming there are 4 classes in this problem. So yeah, any questions with regard to our multi-class model? Okay, so there's nothing in chat. And also, if you have like a question at any point, feel free to speak up, because like it's kind of difficult for me to monitor chat while writing on an iPad. Okay, so there is a question. So W transpose is a 4 by 1024 matrix. Yes. So here, I'm assuming Pix is 1024. So yeah, this would also be 1024, 1024. Yeah, so yeah, thanks for that clarifying question. if there are no other questions, I'm going to move on. Oh yeah, here's a quick poll. This might be slightly challenging, but hopefully if you've been paying attention, this shouldn't be too challenging. So in multi-class classification with F features, C classes, and M training samples for X, the W will have which of these following dimensions? I'm gonna give you guys maybe like 30 more seconds. Feel free to refer back to our previous slides. Okay, so the response is unanimous. So that's correct. It is F by C. So hopefully that makes sense. All right. All right, so let's talk about our activation function for the multi-class setting, which is softmax. So softmax is actually a generalization of sigmoid to multiple classes. So it should look a little familiar, even though it's not completely the same. So our softmax function, recall, takes in our logits C from our model, which we got from taking the product of W transpose by X plus B. And it outputs our predictions Y hat, which basically is a probability distribution for each class. So it's this thing here. So because it's a probability distribution, all the values in Y hat should sum up to 1. And each value here should also be positive because we're non-negative, because it can also be 0. So yeah, let's go through, let's walk through how softmax actually works. So, excuse me. So the first step in our softmax is to exponentiate like each of these numbers in our logits. So 3, we should exponentiate, so we get e to the 3. And then we get e to the 4 for a second number, or e to the 1 for a third number, and e squared for the last number. So after we exponentiated, this should remove any negative values. And then the next step here is to perform this very scary operation. It's actually not that scary. So this is basically just taking the sum of all the values in my exponentiated vector. So let me compute the sum. So e cubed plus e to the 4th plus e squared. So this is my sum. And so essentially what I want to do is normalize this vector. So I am going to get, so I'm just going to multiply by the reciprocal of S. So this should ensure all the elements in my vector adds up to 1. So if you actually work out these numbers, you'll get, you should be able to get like these values that we have on the slides. So I guess it's also useful to think about like what these numbers in our Y hat actually represents. So the first number here is the probability. that our label is a cat, given the image that we see, which is X. And the second number here is the probability of our label being a dog, given the image that we see. And the third number here is the probability that our label is a chicken, I believe, given the image X. And the last number here is the probability that our label is a fish, given the image. So yeah, this is quite similar to what we have for binary classification. So yeah, these two should be related, which has this really nice interpretation. So yeah, that's basically it for softmax. Here is a more, here we generalize softmax to C number of classes as opposed to only 4 classes. So to summarize, to convert our logits into probabilities, we first exponentiate each of the values in our logits C, and then we divide by the sum of the previous vector. So this is just the normalizing step to make sure that all the whole vector adds up to 1, because it's supposed to be a probability distribution. And this gives us our y hat at the end, which is this final vector that we have. So this is the final prediction that our model should output. Again, this makes sense because there are like C values in our y hat, and recall it for our one-hot encoding. Our one-hot encoded label is also a C by 1 vector. So it's going to look something like this. So since our y and y hat has the same shape, then that makes computing the loss a lot easier. All right, so any questions with regard to softmax before I move on? Okay, so this is a good question. So why do we use exponential in softmax as opposed to so it's basically, so why do you apply the exponential term here as opposed to some other function? Because the exponential might seem kind of ad hoc almost. So there are a few nice properties that e to the x has. So the first property is pretty intuitive. It's e to the x is always positive. And recall that our output is a probability distribution. So we want each of the elements in our output to also be positive or non-negative. So yeah. And the second property is that e to the x is monotonically increasing. So what this means is e to the x is strictly increasing over its entire domain. So it might be slightly less intuitive why this has to be the case. So let me go through a counterexample. So I'm going to try to draw x squared. So x squared is also always positive over its, or non-negative over its entire domain, but it's not strictly increasing. So if we pick 2 numbers in our x squared, so let's say -200 and 200. So this would, so f of -200 would actually be equal to 200. And if we use this as our function for softmax, this would not work because when our logits is like really negative, like that means it's very unlikely that our model, it's really unlikely that our model should actually predict that class, because a negative value means the model doesn't really think it's the correct class. Whereas if the logis is really large, that means it is very likely that the image is actually in that particular class. So if we use e to the x, f of -200 would be all the way here, which is close to 0. Whereas f of 200 would be a really large number. So that makes sense because we want our, so yeah, that basically matches what our assumption is, which is if our model predicts a really large number, then that means it's very likely that our image is actually in that particular class. And the last reason is not really like, I guess, like doesn't have any like theoretical proof behind it, but it just works well empirically in multi-class classification. And if you actually like read some of the ML papers, like a lot of the neural network architectures like have this softmax layer at the end if it's performing multi-class classification, just because it works so well. And it's kind of like the industry standard for tackling multi-class classification. All right, so I guess if there's no questions, we can move on to the cost function that we're going to be using for multi-class. If there are any questions, feel free to type in chat or speak up. Also, like, I'm wondering if like what I'm saying actually makes sense. So if it makes sense, please react. Maybe do like a thumbs up. Okay, I see 3 thumbs up, so that's good. Okay, so for multi-class classification, we need a loss function that can generalize to an arbitrary number of classes, which in this case is C. So this function is called cross-entropy, or more specifically, categorical cross-entropy. And the intuition behind cross-entropy is that the cost will be higher if our model makes a bad prediction. So what that means is the probability of the correct class is far away from 1. So for example, if our label is a cat, which is 1000, so a good prediction would be 0.9, 0.1, and then 00, because like the difference for the correct class is really small. Whereas a bad prediction would be, let's say 0.2, and then 0.5, and then 0.3, and this would be 0. So this would be an example of a pretty bad prediction because our model thinks there's a 20% chance that our image is a cat when the image is in fact a cat. Okay. So here's the equation for our cross entropy for a single train example. So let me write that down. So this is only for a single train example. And we call the label, or the one-hot encode label for our image here is going to be a C by 1 vector. And that the prediction is also going to have the same shape. So let's actually break down this, this summation, which might be a little bit scary. So let me expand this actually. And so if I expand this, this would be negative y0 times log of y hat of 0 minus y1 log y hat of 1, and then y2 and y3. Okay. And if you actually look at this vector here, so actually only y1 is a non-zero, right? So we know y0 is 0 because this number is 0. Y2 is 0. Y3 is 0. So this actually only simplifies down to one term. So here, the only class that will contribute to loss is the class that has a 1 in the label, which in this case is y1. So let me highlight that. So it's this term. And so to minimize the cost, our model just need to make that corresponding class in y hat as close to 1 as possible. So we want to make y hat of 1 as close to 1 as possible. So yeah, that's basically the intuition behind how we want to minimize our cross entropy. And so recall this is only for a single string example. So in machine learning, we want to compute the total loss, total cost across all training examples in our training data set. So this basically is just a matter of summing over all the training examples, which is this summation over here. We also want to take the average because we don't want the cost to essentially blow up, because like usually in most machines, there's like a limit to how large like a number can be. So if M is really big, you're going to encounter like problems like integer overflow or floating point value overflow. So we want to divide by M. So yeah, so this term here is basically this here, but we also added like a subscript J, which iterates over all the training examples. So let me write this down. J iterates through all training examples. And then if we expand this, we get this, which is exactly what we have in the previous slide. And then we have another subscript I, which, so I iterates through all classes, which in this case, there are C number of classes. So we iterate through all the classes to compute the loss for one example. But recall, like all these values, or most of these are going to evaluate to 0 because there's only one in the label. So yeah, I think, is there any questions for cross entropy in general? If not, I'm going to pass on to Naman, who is going to discuss gradient descent and multi-class classification. So let me stop sharing screen.
Awesome. Can you guys see my screen?
Yep.
Yeah, you're good.
Awesome. So I'm going to be going over gradient descent in multi-class classification, and then we're going to be taking a look at a code demo where I understand we didn't have our previous workshop live. So what we're going to do is probably cover a bit of binary classification in the code demo, and then also take a look at multi-class classification. So gradient descent, like Claire has already brought up for binary classification towards the end. Now, how gradient descent for multi-class classification works is that it's pretty much the same. All right. We've seen that for binary classification, the gradient descent is sort of an adaptation, but it's actually really similar to linear regression's gradient descent. And it's actually the same as multi-class classification gradient descent. Now, of course, why is this? Like Jensen talked before, softmax is a generalization of the sigmoid function. And the cross entropy loss that we looked at is a generalization of the binary cross-entropy loss that we looked at before. So since both of our current activation function and loss and cost function, since both of these are generalizations of the same thing that we had in binary classification, our gradient descent, our derivatives, they stay the same. And yeah, we calculate the minima in the similar manner. So I'm going to put it all together for you here, what multi-class classification is. So first off, we looked at a cat. Okay, now this is 1, 0, 0, 0, the matrix. So the matrix is 1, 0, 0 because we saw that 1 is for the second is for dogs, the third was for, I think, chickens, and the fourth one was for fish. So we categorize this as 1, 0, 0, 0. And of course, we put this, we look at the pixels in this particular image, and then we throw it into our linear model. Our linear model returns an output, which you can see here is the matrix 3, 4, 1, 2. And then we run it through our activation function, which is softmax here, which is, again, like I've said before, a generalization of the sigmoid function. And it returns us probabilities. Now, keep in mind, how these probabilities work, of course, are for every one of the categories. I mean, all the categories will always add up to 1. That's how probabilities will work. And like we see here, so the probability the first category is 0.24, of the second one is 0.64. So what we see here is our model is actually classifying the image as a dog because our second category was a dog. So I guess we can say that our model is wrong right now. So yeah, so then we run it through cross entropy and we get the loss. Now, of course, it doesn't stop here. We go on to update the weights and the biases, but this is a general picture of how this operates. So we have the pixels, we put it into our linear model, which gives us an output. Now we run that output through an activation function, which is softmax, and we receive probabilities. And after that, we run it through our cross entropy function, and then we get the loss, which is 2.4. And once all of this is done, we go on to update the weights and the biases. So a quick poll, and I'm going to launch this here, but it's pretty simple. Your model outputs the following probabilities for multi-class classification with 5 classes. There are 5 classes, and there are four probabilities. Now, we know that the probabilities add up to a specific number, so that makes this pretty simple. But yeah, go ahead. I'm going to wait for a couple of seconds, and then going to give you 20 more seconds. All right, so yeah, so we've gotten an answer, and of course the answer is 0.1. You add these 4 up and you'll get 0.9. So since all the probabilities are supposed to add up to 1, this is a 0.1. So that brings us to the end of the poll. Now we're going to look at multi-class classification in code, and we're going to hop onto this demo. Claire or Jensen, if you don't mind, can you probably drop this in chat? And we're going to use Collaboratory, which we've been doing for a while now. So if anyone's unfamiliar, please feel free to unmute at any point and talk about it. We'd be more than happy to assist you. Again, if there are any questions about theory all through the presentation, feel free to unmute at any point of time. Or of course, drop it in chat. I will be monitoring chat as well. And yeah. So hopping onto the demo right now. So this is a binary and a multi-class demo. So of course, we're looking at 2 different types of, we're going to look at 2 different architectures here. So how it works is we're going to be working with our iris dataset. So I'm assuming a lot of you are familiar with the iris dataset now. It's one of the most popular datasets in machine learning. and it has 150 data points. So it makes so the size and the quality of the data actually makes it one of the best data sets for machine learning. It's not too big. It's just the right amount that helps us run a lot of functions and experiment around a lot. So that's what we're going to do. So in the first cell here, we're importing stuff in. So we're importing NumPy. And don't worry if you don't understand any of the code. I understand some of this might seem, a little difficult right now. It might seem a little scary right now, but we'll be going over NumPy and Pandas, two of the most, and maybe even some more libraries in our next workshop. So all of this will make a lot of more sense once we go through this. Right now, I just want to show you how our model works. So we're just going to be going through this code. You're not expected to write it right now, but yeah, over the next couple of workshops, we'll teach you how to, and you'll be writing this code yourself. So we import NumPy, which is the library we use for our numerical calculations. And then we have matplotlib, which we use for plotting graphs or all types of statistical models. Then we have scikit-learn, which is practically the bread and butter of machine learning. This helps us run sort of pretty much all the functions that we do in our models. So and we import three things, which we'll be going over. The last one is iris, which is our iris dataset, logistic regression, which we've been studying all this while, and train test split, which I will cover as we progress. So first off, we load the iris dataset. Fairly simple, and we know that the shape of the dataset of the iris dataset is 150,4 because there are 4 different features that we look at, and there are 150 data points. But what we're going to do here is we're going to drop the last 2 features. We're going to look at this in a 2-dimensional way just to simplify it for all of us. And yeah, we have x is equal to x. And what we do is we put a colon, and the second parameter is a colon 2, which helps us to drop the last 2 features. So now we get a 150,2 shape. And now we can hop on to binary classification. So of course, it's binary classification. So we're expecting to have 2 different labels. We're going to classify our data as 2 different labels. So in the iris dataset, all of our data has a label. There are 3 primary labels. So there's 0, 1, and 2 over here. And what we're going to do is we're going to drop the 2 labels so that we have just 2 labels instead of 3. So of course, we convert to binary first. And what we do is, so like we went over in the Intro to Python workshop, this stands for not equal to. So for y not equal to 2, we take in the functions, and therefore all the function points which have the label 2 are dropped off. That leaves us with everything with the label 0 or 1. So we move on, and now we just have, we're looking at binary data here. So then there's the x bin, y bin. What this function does is talk about the shape. Now that we've converted it to binary, we look at the shape, and for x, it's 100, 2. And for the y bin, the shape is 100. Yeah. So we define the plot data here, and most of this is just messing out with the plot. It is talking about the length and the size of the figure. But we're looking at class 0, 1, and 2. Of course, we'll be omitting 2 when we talk about binary classification. And then we plot this data on x bin and y bin. So this is what our data looks at right now. And now we're going to try and build a regression model out of this. So we've plotted our data of class 0 and class 1. So class 0 is the blue dots, and class 1 are the red dots. And naturally, since this is binary, we've dropped class 2. We will be seeing the green ones when we hop onto multi-class regression, but we're going to avoid it for now. So split data into train and test data. Now, there's the x train, x test, y train, and y test. Now, what is all of this? So I'm going to take you over to the
Okay, so there are some technical difficulties. I think Naman is dropped out. Okay, I think he's
Hi,
back, right?
I'm so sorry. My laptop crashed.
No, you're good.
Not the best time to crash, but yeah. I'm gonna share my screen again and let me know what you see. Yeah, so can you see my screen?
Yep.
Yes.
Scikit-learn that word.
Perfect. So we're looking at train test split, which is one of the best scikit-learn functions that we're going to be implementing right here. And we've used this before, so some of you might be familiar with this from the linear regression workshop. I think we even use this in the KNN workshop. I'm not too sure, but yeah. So what the train test split function does is it splits the eraser matrices into random train and test subsets. So when we deal with classification, like specific, we're looking at matrices all through. Like over the past 30 slides, we've seen at how we've been working with matrices. So what we're going to do here with our scikit-learn function is we're going to split it into random train and test subsets. So over here, yeah, we have the X bin, the Y bin. Now, these are the bins that we've created, that we've optimized, that we've processed. And we have test size and random state. So these are mostly arbitrary numbers, but yeah. So the test size takes a float or an int. We covered these data types in our first workshop. And it should be between 0 and 1 and represent the proportion of the data set to include in the test split. So what this does is this splits the data and it tests a specific part, trains a specific part. So how it works is usually when you enter a test size or a train size, so if you enter one of them, the other one automatically complements the other. So if your test size is 0.2, your train size will automatically become 0.8. So you don't need to set both of them, but they add up to 1. And if we don't enter either, the test size is usually taken to be 0.25, which is 25% of all the data points. And apart from that, we look at random state here. So I've set random state to 9. Again, you can set it to 50 or 80 or any other number that you like. But what it does is it controls the shuffling that is applied to the data. So it's like a pack of cards. You shuffle the cards as much as you want. So how much do you want to shuffle it? And then you take out the test size and the train size and you work on them. So of course we pass an int here. And yeah, that should be it. Now going back to fitting the logistic regression to X train and Y train. So this is it. Now, everything that we studied all across binary classification, it comes down to this one line. Okay, we run logistic regression, which we imported from scikit-learn over here. And yeah, that does the trick for us. So our binary model, this is the variable that we're using to define the logistic regression fit. And we enter X train and Y train. So we fit the logistic regression to X train and Y train. Now we print the accuracy on the test data. So what we're doing here is we set the accuracy to the binary model's score. So the test accuracy is actually the score of the model. So right here, what I'm getting after running this is a test accuracy of 0.95, which is 95%, which means that the model isn't entirely accurate. It isn't giving me 100% accuracy, which means there are a very few number, but 5% of the data points are outliers. So if we see this and I try to draw a regression line over here, we can probably see that this particular data point seems like an outlier if we try to draw a regression line here. And we will see that once we do it. So now, of course, we can get the accuracy, we can get the weights, and we can get the bias. Okay, so these are the weights of the first type for the first category, and this is the weight for the second category. Now, of course, weights can be negative as well. And similarly, the intercept, which is the model's bias, comes out to be minus 7.07. And now what we do is we plot this data. So we plot the decision boundary of the model by running the slope and the intercept. And this is numpy.arange. Now how this works is this returns all data points at even positions. So we'll be doing this again over the next workshop, so you needn't worry about this right now. but the y plot becomes the slope times the x plot plus the intercept. So this is the slope. Yep. So the y plot is, in short, what we covered before. It's wt times the x plot plus the intercept, which is the bias. And when we plot this, we get this. Now, of course, here c is equal to black is just the color, and we label this as the decision boundary. So this is the decision boundary in the legend. And once we plot this, we get this sort of a division, okay? And that seems pretty neat. So yeah, we have our data classified, and yeah, that's what it seems like. So we have a decision boundary. We have a class 0 and a class 1 here, and it's classified evenly. Now, are there any questions? I don't see any in chat, so I think we can move on to multi-class classification. I'm going to hold up for a couple of seconds. Yep, so I think we're good to go. So let's look at multi-class classification. Now, this is more or less similar, I'd say, in a way. So here we plot the data, and this time we don't get rid of everything with the label 2. So we have 3 different bins that we can categorize our data into. There are 3 different labels, being 0, 1, and 2. So class 0 here is represented by blue, red by 1, and class 2 is represented by green, which we didn't see before. Now, again, we do the same thing. We run a train test split, which we did before. We know what it is. We know how it works. And we take the test size to be 2, which is usually considered a good test size. Again, the default is 0.25. So always keep that in mind. And the random state is 9. Now, if the test size is 0.2, the train size naturally becomes 0.8. Now, we train the multi-class model. So again, this is what it is. This is the logistical, this is, again, the one function, the one line of code that makes our model again. And it's the multi-class model. It's the same, it's a similar function. That's exactly what it looks like. And I think our previous one looks like the same. And then again, we have to print our accuracy now. So we look at accuracy, and it's the model score. And this time our accuracy is coming out to be about 0.93. And we get the model parameters. So the model weights this time come out to be, again, 3 different elements, and we get 3 different biases here. So that's how it is for each label. So each label has 2 weights and a bias. Now, we visualize the results. That's what we're doing here. And we run a bunch of functions. We create a mesh grid here. And what we see here is a color plot, all right? Again, most of these things are similar. We'll be covering this in detail in the future, but what we're looking at here is a multi-class classification. Okay, this is what it looks like. And like you might see, the decision boundary cannot separate the data perfectly. Okay, so the accuracy is lower than 100. That's how it's going to be, because we see that there are a lot of data points which can't be separated by one large regression line. So what we get here is a few mixed data points. So we can't entirely classify, like, if all of these points in the red portion were actually green, and if all of the in the yellow portion were all red, we would have had 100% accuracy. But due to the nature of our data set, we can't attain 100% accuracy on this particular model. And yeah, that brings me to the end of the demo. In case there are any questions, I'd be happy to take them. So feel free to unmute or drop them in chat. But yeah, apart from that, there's the feedback form. And next week, we'll be covering NumPy and Pandas. We might go over a few other libraries as well. And yeah, that's Kung Fu Panda, but that's not the Panda that we're looking at. It's a machine learning library. We'll also be exploring a few more. So we'll be going over some important machine learning libraries before we delve into the guided project. And in the guided project, we'll be using all of these libraries and all of these concepts. We'll be putting it all together, and we'll be helping you debug the code that you write. Apart apart from that, there's our Facebook group, there's our Discord. I think everyone has the slides link as well. So that brings us to the end of this presentation. We'd be happy to take any questions whatsoever.
Yeah, thank you for coming. Okay, that's everything.